Welcome back, everybody. If you can come back into the session as quickly as possible. We have a series now, session 3, selecting targets for slope stability assessment. I'm sure you are really interested in how we go about this. So there are 3 talks coming up, all by Andy Fourie. He's first going to talk on limit equilibrium modeling, deformation, and liquefaction triggering, and how we select targets for that. So over to you, Andy, and thanks again for all your efforts and preparation.
Thanks, Andrew. Good morning, everyone. I think most of you were here yesterday, but for those that weren't, hello to you. Just before I get into this, we heard a bit about what the limitations of the limit equilibrium method are, particularly with kind of progressive type failures. There's a famous case of the Carsington Dam in the UK where they only kind of explained the phenomenon through use of numerical modeling. So, that's all well and good, but I guess I would just caution against any kind of thoughts that we can just jettison limit equilibrium methods and move on to this brave new world, sort of unshackled by limit equilibrium methods. They're based on a lot of experience. There's a lot of kind of intuitive understanding that I guess people have with using limit equilibrium. And the other thing is, we were talking about this last night, trying to convince the regulators to accept numerical modeling as the be-all and end-all is going to be a tough ask. So I think as we progress, I would imagine looking back, 5 or 10 years' time looking back, limit equilibrium methods may be just like a check that's finally used. Other methods have transcended it. But to get to that kind of position, I think we have to take everybody along with us and perhaps be running multiple analyses showing how the limit equilibrium results compare with whatever this new technique is that people eventually kind of settle on, I believe. So I think it's an evolving approach, but let's not think we can just blithely move from one to the other without taking everyone along with us. So, talking about limit equilibrium methods, now this is a flowchart. I said recall the flowchart. In fact, it's preceding the presentation on the flowchart that's going to be given directly after my 3 presentations about different cases and how to deal with them, dilative versus contractive and so on. I'm not going to dwell on that, but just hopefully there's some links with that, and then also with what was said by Mauro. Now, in terms of the types of stability analyses, to maybe try and encapsulate it in the way currently used often, a drained analysis that's appropriate to dilative soils, use effective stress parameters. There's no excess positive pore pressures present from shearing. Maybe you can use limit equilibrium using the friction angle, target a factor of safety. And that's what's called for in the current documents, things like SANCOLD, etc. Undrained, which some people have kind of taken a while to accept, is assessing the likelihood that contractive undrained shearing could be initiated. Could do limit equilibrium, increasingly numerical modeling, we see. We've had a student recently do some comparisons using 2 different software packages on a calibrated Norsand model, and you don't get the same answers. So we do have to be a little bit interrogative of numerical models. If you use limit equilibrium using peak undrained shear strength, you target a factor of safety of 1.5 again. And then post-liquefaction, I prefer the term large strain, but it's assuming that the peak strengths have been exceeded. And we've generated positive excess pore pressures in that process, initiating some form of strain softening. Currently, limit equilibrium is the go-to, but this is where things get quite gnarly, and where I think we're going to maybe have some debate today is what target factor of safety do we use, what strength ratio do we use, how do we derive it, etc., etc. And the implications of it, which I think some of you are all too painfully aware in terms of costs of buttressing. But this is where we are currently, right? So it's by far the most widely used method at the moment, most widely used approach. Most design offices will have people working on stability analysis using limit equilibrium, but it does suffer from limitations. And we've heard some of them today, and that's particularly for looking at soils that are brittle. And again, what is brittle, and what is merely strain softening is perhaps another long debate. But when you're talking about this progressive failure or static liquefaction, then they do have these limitations, certainly. And specifically for highly brittle tailings, which I take to be tailings that lose that strength over a very small amount of strain, then you have very significant stress redistribution. And then there's also the lack of accounting for different strengths. And again, Andy was mentioning that in terms of the Mount Poly, that you've got different stress strain curves. So you maybe a very kind of brittle tailings overlying a ductile foundation. So there's all these limitations, but sometimes these limitations are not perhaps as restrictive, and you can use limit equilibrium with a little more confidence. But nevertheless, we do recognize these. I think it's also just useful to point out, let's go right back to some basics here, is what we're assuming when we do a limit equilibrium analysis, essentially. There's often, at the very start of kind of understanding soil mechanics, there's two approaches, a limit analysis and a deformation type analysis. Now, in terms of a limit analysis, what we're actually assuming is, as shown by that little sketch on the bottom there, is that you have this limiting strength condition, but you undergo no strain, no deformation to mobilize that strength. So in other words, as soon as you mobilize that strength, then you get infinite deformations, essentially. So it's a completely what's called a rigid, perfectly plastic material. So it requires it makes no kind of assumptions or no predictions about the deformations of the soil mass. It's purely this something in space that's just been subjected to stresses, and once you mobilize the limiting strength condition, that's when failure occurs. And as Mara was showing you, implicit in the assumption is that you get the same strength mobilized at the base of every slice, which we know is certainly not the case for brittle type failure. Undrained strength, just expressed, that way, the maximum shear stress is the undrained shear strength. Often we then normalize that with the vertical effective stress, and thankfully software programs these days can incorporate that pretty successfully, because you do get this effective consolidation with depth, sample gets denser, hence undrained strength is greater. Contrast that with the drained strength, where we have these two components. I think everybody's familiar with that. But then again, that bottom statement is something that Louis kind of touched on yesterday. The key to having a drained condition is the fact that the shearing is applied at such a rate that the excess pore pressure generated can be dissipated faster than the rate of load application. So in a sand, normally, if you're applying a shear stress, building a high-rise structure, the rate of construction is such that the pore pressures dissipate far quicker than the rate of loading that's applied. But if we apply the load faster than we can dissipate, we can still get these excess pore pressures in sands, and hence we get undrained type behavior, that shear-induced pore pressure. The second way of thinking about a soil, certainly to start with, the initial approaches, was to think about a deformation analysis. You've got stress and you've got strain, you've got the Young's modulus, the relation between them. If you do a simple elastic analysis, there's absolutely no limit, though, on the amount of stress you can generate. You don't have a condition. So we all know soil's completely different to that. We get maybe a elastic, pseudo-elastic behavior to start with. We get a peak strength, maybe a large strain strength, etc., etc. I'll just superimpose those two simple models, the rigid body and the elastic, on that. But, we have to actually have something that incorporates both of those. And not only that, but take account of changes in volumetric strain, that is the bottom curve there, volumetric strain over, or change in volume of initial volume, or change in pore pressure. So it gets far more complicated. So so-called real soil behavior, limit equilibrium says nothing about that. And as Mara said, implicit is the fact that the strengths are mobilized equally throughout the failure surface. So can FLAC or other software provide some insights? Clearly you can utilize a much more realistic stress-strain behavior. You can include strain softening. Now you can include this through kind of forcing it to behave in a certain way, or you can have it incorporated in the model itself, such as the NORSAN model. And you can also use it to get factor of safety estimates using a strength reduction method, which can be very, very powerful. But that's usually when you use a simple model such as more Coulomb. And I think one has to be cautious with the strength reduction method as well. Again, much like limit equilibrium, when you have soils with different stress-strain characteristics. Because if you think about it, you're usually reducing the strength equally through all soils, but some of them mobilize peak at much different deformations than others. Nevertheless, let's look at a simple hypothetical tailings profile here. We've got an undrained strength ratio of 0.25 below the phreatic surface. You then loop through this and you reduce the strength and you get a factor of safety of 1.29, that predicted potential failure surface. Running a optimized Morgenstern and Price with profiles, strength profiles in that green wedge, it's the contractive zone, 0.25. Above it, just assume drain strengths, which is I think what many people do. And you get 1.26, so that's pretty good, right? So you get that agreement. But again, as soon as you get more complex geometries or zones, etc., the strength reduction method is not necessarily going to give you exactly the same answer. So you can use the FLAC to perhaps locate the most likely failure surface, and increasingly limit equilibrium is maybe giving you more flexibility in getting the most likely failure surface as well, for simple cases, right? But in these terms, they don't account for the stress-strain behavior and certainly not brittleness, even the more Coulomb strength reduction method. We'll hear probably more about this a bit later on. This is the ICOLD bulletin looking at different stress-strain behavior. They've got three zones. They're highly brittle up to generally non-brittle. So you might have the same normalized peak strength, but you're getting very different post-peak strengths. And I think, well, we mentioned the Bishop's Brittleness Index yesterday, but I think there's a lot more to that, and that's what happens post-peak, and how do we characterize that adequately. And the reason I say that is I've got two sets of results here just to illustrate the point. So the one on the left is from some work done on the Merriesprate tailings many years ago now. The box at the top there is just the void ratio. These were K0 consolidated, and you'll see that the peak strengths were reached at, it's really hard on this figure to detect the axial strain, probably 0.2, 0.3% axial strain, and then some strength loss, giving you a brittleness index according to Bishop of anywhere between probably 0.5 and 1. But consider the one on the right-hand side. So this was, again, K0 consolidated. It's a red mud material. You mobilize the peak at a small strain, but the post-peak behavior is very, very different. So are those equally brittle? I don't think so. It's the strain over which the strength loss occurs that's crucial. And this really comes to the point of monitoring. Which of those would you be comfortable having confidence that you can monitor for incipient failure and post-failure conditions, and which would you not be? We hear a lot about INSAR. Here we've got three sets of data that we processed. The top set of 3 lines was from a gold tailing storage facility in WA, where we're getting displacements, and it's substantial time that we have this data. The bottom solid curve is from Zelazny Most in Poland, probably the biggest tailing storage facility in Europe. And then the one in between, the 3 lines there, are various measurements made at Feijão or Brumadinho. Now, there's been claims that the failure at Brumadinho could have been predicted using INSAR. I'm not sure on what basis they're always made, because the one below is experiencing much greater deformations, and it's still standing, and it's a very significant structure. So in the absence of tying that to accurate deformation modeling and being able to predict the potential failure on that basis, I think one has to be really careful again of these kind of approaches to supposedly monitoring to ensure safety. So just to note, limit equilibrium tells us nothing about deformation. It can't account for strain softening and progressive failure. And early detection of developing instability is a real tough one with current technology. I'm not aware of any technology currently available that we can use to detect an impending potential failure triggering occurring in highly brittle materials. And be interested if anybody else has thoughts on that. I'm going to keep moving because I've got to get through 3 presentations in a fairly short space of time. So if we could bring up the next presentation, the deformation one. There we go. Wow, that was quick. Thank you. So moving on to deformations and thinking about targets, etc. Here's some data from a clay-like tailings, direct simple shear tests. These had different biases imposed. Talked about bias yesterday. That's when you consolidate it in the device under some imposed shear stress. So it's not just K0 consolidated. And you'll see again, you get very different behavior. If it's just the bottom curve is when it's zero bias, K0 consolidated, you get a peak mobilized at a strain there of probably 25%, and then gradual loss in strength. Whereas if you've consolidated under bias, you get a higher undrained strength ratio, but post-peak, it's kind of much worse because you're getting a much more significant loss in strength with strain. So setting targets for perhaps monitoring, doing the tests that capture the right behavior is going to be really crucial. And in this case, eventually they kind of converge perhaps on a large strain strength, but we still haven't stabilized. We still haven't got to a limiting condition in this case. Now, the DSS, we see that being used a lot for predicting large strain strengths. But the trouble is, you really don't mobilize a lot of displacement in the direct shear apparatus. People have used it in the same way as the old style direct shear box was used, where you shear it in one direction, then you reverse, and then you shear it in the other direction, and go backwards and forwards. And that's one approach. But I think, as with the old style shear box, you get a lot of particle rearrangement, and you get a lot of sort of peaks and troughs. It's very non-uniform. We're also finding that when we compare direct shear results with hollow cylinder results carried out under the same stress path, that the hollow cylinder shows you much lower large strain strengths. And that's another entire debate. But here we've got some data from shear vanes done on the same material, and then the blue line is using what's called a constant volume ring shear device. So there you can do kind of large strain, undrained shear strength ratios. And then you can see quite similar peak values, but in 2 cases you're able to monitor and actually get some handle on the large strain strength. And interestingly enough, for this material, those are at strength ratios way higher than we sometimes see in the literature for clay-like material, but 0.15, maybe 0.13 for large strain strengths. And incidentally, the kind of remolded vein, where the vein was turned at high rates of rotation, we're giving about 0.12. So DSS is, I think, great for getting peak strengths, but it has to be used with caution to use for large strain strengths. So there's significant differences then in the stress strain behavior that we're getting from those plots. That could be from a number of factors there. I won't dwell on those, but I guess as we explore these different devices that are now becoming commonplace, perhaps some numerical modeling of the devices themselves is actually required to better understand what's going on. There's also, we know also that you can get different stress strain post-peak type behavior depending on the rate of shear. Talked yesterday about the need to shear the vein fast enough to make sure we get undrained peak strengths. But then what about undrained large strain strengths? Do we need to then change the rate of shear of the vein during the test itself? There's not a lot of data in the literature on rate effects on the large strain strength. So we need to, as I say, we need to ensure that the vein rotation rate is capturing peak undrained as well as large strain undrained. And people are doing it at very high rates, 720 degrees a minute. What's it at? Compare that with the conventional rates, that the vein is specified at, much, much higher. But just note that that's then applying a shear rate which is much faster than we'll probably see in a failure condition in the field. So is that perhaps being unrealistic in terms of rate effects again? So when setting these, or when thinking about these, the need to capture this post-peak behavior, there's a lot of complexities involved. I've mentioned this constant volume ring shear device. So it's similar to the ring shear I talked about yesterday. The trouble with a conventional sort of bromhead type ring shear device is that as you're shearing the material, it can either dilate or contract in response to the shearing. So you're getting a change in volume. The constant volume ring shear device keeps the volume, as you would expect, keeps it constant by keeping the height constant. It's a tricky device to use, but then we can start looking at rate effects in a more controlled manner. And perhaps this is, by comparing this device with many other kinds of devices, vein, etc., we can start choosing these large strain strengths more rationally in the future. So here we've got some data. This is large strain strength ratio against what we've called peripheral velocity. So it's trying to relate the velocity at the tip of the vein, or the edge of the vein faces, so converting that to a velocity, and comparing that with the ring shear, the constant volume ring shear. And you can see that the agreement there is really not bad when you look at, or when you compare it with a lot of traditional kind of plots of strength. That variation of 0.02 or so on is really pretty good, but it's also indicating the effect of shearing velocity or shearing rate on the peak undrained shear strength. So you're probably getting some kind of small viscosity effects there. So thinking about brittleness and how we accommodate that, flak using more Coulomb is not really that much better than limit equilibrium when dealing with brittleness. But what David did here is play with the model to include some strain softening, but in a pretty simple manner. Now, within flak and using more Coulomb, so not Noor sand, you have this ability to kind of do some sort of pseudo strain softening. You can decrease the cohesion, you can decrease the friction angle with some measure of plastic strain. Now, this is not meant to indicate this is realistic behavior. This is indicative behavior of strain softening. So keep that in mind. But if you look at different versions of that strain softening, so same peak undrained shear strength, SU over sigma V dashed of 0.25, and same post-peak, 0.1, but different strains to mobilize that large strain. So what do we get? Well, firstly, to point out that it's now effectively a range of brittleness, if we use the term brittleness to include the kind of strain over which the loss of strength occurs. But just emphasize, identical peak and post-peak. Identical initial elastic modulus. Also to point out that a lot of laboratory tests, it's really hard to get beyond about 30% strain, probably 25% strain. And so we can sometimes lose that kind of behavior I'm indicating here. But what was done is to activate these different strain softening models in the contractive zone of that hypothetical problem showed earlier and see what happens. And in fact, it becomes very dependent on that rate of loss of strength. So the wording that points to the two left-hand lines on that figure, I'm conscious again of green versus red, that's why I'm not referring to it. But the slope actually failed. And you got full mobilization of strength, you got a kinematic mechanism developed. Whereas the two on the right-hand side that showed the same loss of strength, it didn't fail. Mobilized quite large displacements and had a zone of plasticity developing where the strength was mobilized, but it didn't propagate throughout. So this is perhaps giving us some confidence in the concept of using numerical modeling, because we can capture this behavior, and it can sometimes lead to a situation where we don't get outright failure occurring, but then we have to have absolute confidence in the numerical model, and I'm afraid we're not there yet. And I really think selling that to regulators is going to be difficult. But I think if we went through a process of these kind of simplified illustrations, compare it to the limit equilibrium, and then show that to people, we can start getting a bit more buy-in from all the kind of groups that matter. And just incidentally, superimposed on that is kind of some so-called real data, Mount Poly, that dashed line, that behaved very much like that less rapid strain, or less rapid loss in strength, whereas the silicafine sand that I've referred to before yesterday, or the standard laboratory sand we use for a lot of our sort of model calibrations, is even more brittle than the most left-hand of those curves. Now, it's limited. I mean, that stress strain behavior was kind of turned on somewhere through the modeling. If you'd built it up in layers, trying to reproduce some kind of realistic history, it probably would have been different, because you would have had some localized strain softening and then perhaps reconsolidation, etc. So these are all aspects that a realistic numerical model may need to capture. But that aside, I think it just illustrates the key point I'm trying to communicate, which is, let's be clear what we mean by brittleness. It's not just the Bishop's brittleness index. It's the strain over which it occurs. So maybe it would be better to model the life of the slope. That can be really tedious, because you're trying to work out what the deposition rates were, when, etc., etc. But then we can use a constitutive model that captures this behavior organically, rather than kind of in this false way that we've used here. So rather than forcing it. And people have their preferences. A lot of people prefer the Norsand model, but there are people who prefer other models. And again, let's make sure we perhaps calibrate them realistically, not just based on one set of triaxial laboratory data. But then that could also be coupled with fluid movement, some kind of completely coupled stress strain model where you get the migration of fluid at the same time as you're getting changes in stress conditions. So, key thing, as I've mentioned and Nara's mentioned, a few people, we don't capture this behavior with limit equilibrium. That is a severe limitation. But as we'll see in the next discussion as well, deformations such as in the basal extrusion failure mechanism are absolutely key. So, some just concluding comments on this discussion. Post-peak deformations, they can dictate stability. Once you start mobilizing that reduced strength, clearly. Not all laboratory methods capture this adequately at the moment. And again, I want to keep emphasizing this. Be careful about trying to monitor for something that at the moment is inherently just, I think, impossible. We just don't have the technology at present. Okay, so then I think we're just about on time for the final presentation, so if we can bring that up. Now this could be a half-day talk. I'm cramming it into 20 minutes, and I'm trying to save a little bit of time for Alejo because I know he's got a lot to get through as well. But let's talk about liquefaction triggering a bit. So I showed this slide yesterday. On the right-hand side is the illustration of the concept of the instability line, where you trigger peak strength at a lower value than you get from the failure line from a friction angle, from an MTC type failure. But also that instability stress ratio at which it occurs is strongly related to the state parameter. So you'll see at a state parameter of about of 0, we're getting instability stress ratios of in excess of 1.2 to 1.4. You're getting to the MTC. You're getting the drained type behavior there because you're just about on the verge of dilation, the negative state parameters. But as you get further and further away from that 0 state parameter value, i.e. your state parameter is getting up to 0.1, you're getting a lower instability stress ratio. So you're triggering failure at lower peak, or at lower Q values, lower deviated stress values. So the approach that a lot of people are using with triggering is to think, what are the plausible failure mechanisms that can occur? And there's often 3 that I see again and again. The one is this so-called constant shear drained. So imagine here you've taken the sample up to a stress state, it's K0 consolidated. We had a bit of discussion yesterday about what that K0 value is likely to be, somewhere between 0.5 and 0.7. Then the phreatic surface rises. Now, it's a little bit of an oversimplification to show it as a horizontal line going from right to left, because there's a little bit of sort of reaction in Q due to the unloading. But to all intents and purposes, a horizontal line is adequate. So as we get that stress path being followed, we will potentially get to that instability line, at which point we get this contractive undrained shearing happening, and we can get the runaway failure taking place. So this is the one stress path that we can think about for potential liquefaction triggering. So it's now in terms of these trigger mechanisms, a key feature is that we're actually increasing the ratio of shear stress to effective stress during that stress ratio, during that stress path. So if you think about that, we're going from right to left. The shear stress is remaining the same. The mean stress is decreasing. So we're increasing the ratio. And the higher the ratio gets, the more likely we are to trigger what we talked about yesterday as mechanism 3. The undrained generation of excess pore pressures through the process of shearing. So that's what happens in this rising phreatic surface, the constant shear drained failure stress path. Now, that's one mechanism. What else can trigger it? Well, perhaps placing a substantial new lift of tailings very rapidly is potential because it's increasing your shear stress quite rapidly. It's probably less likely to be a cause. I don't think we've seen too many triggered by lift, but maybe it can't be completely kind of discarded. But anything that increases the shear stress ratio under either undrained or drained conditions is kind of pushing us in the wrong direction. It's pushing us close to that instability stress ratio. And just to emphasize the point made yesterday, you can load it under purely drained conditions up to a point that's very close to, or even sometimes beyond that instability line. But then when failure gets triggered, failure being this runaway generation of excess pore pressures, then you get this really dramatic loss in strength. So let's revisit some of that. So here we've got the instability stress ratio for a particular state parameter of 0.05, so it's positive but not exceedingly so. The solid line is the friction ratio, probably MTC from triaxial compression, some starting point, K naught consolidated. Any one of those stress paths are increasing your stress ratio, Q over P dashed. And what can cause those kind of stress paths? Well, we've talked about the one already, the rising phreatic surface. Okay. And in the Massachusetts dam example, they actually had data showing a phreatic surface, showing the piezometer, and they were able to capture the value of that pore pressure at the instant of failure. And when they did the analyses, it was clearly not a drained failure that was occurring. It wasn't, even though the drain factor of safety was more than adequate, we've got this mechanism, three being triggered, and we had a runaway failure. So it's an interesting case study that was Massachusetts case study. We could have this rapid wall raise, or probably more likely some kind of other material placement. So where you get, and again, it's a simplistic representation of a constant P dashed, but you're getting load taking you up to that instability line. There's the documented failure at Pinto Valley, where there was a TSF over which they were placing a waste rock dump as part of the, closure development. But they were placing it in very significant lifts, really high rate of loading, and triggered a static liquefaction at Pinto Valley. So it's not unknown. And then somewhere, before I get to the lateral extrusion, you could even also have some kind of removal of material at the toe, giving you a change in P dashed. But one that was probably ignored until Fundao, in our community largely, I think, was this phenomenon of lateral or basal extrusion. And the stress path is shown as again, something simplified to be that starting point shown and then progressing to the instability line. So it's actually been around for a long time, and it's like most of these things. Once you start digging, you realize that there's information in the literature that we probably have ignored. The whole concept of static liquefaction, in fact, this paper by Smith in the 1950s. If you go to Tesagi's book, published in 1948, he uses a term called spontaneous liquefaction, which is no different to static liquefaction. But basal extrusion is quite a detailed study on one of these underwater berm failures back in 1998 as well. So even though it came to prominence after Fundao, there is other evidence that's looked at this mechanism as well. So what does it entail? Well, let's think of a TSF on a soft, ductile foundation. You've got an element of tailing shown there. It's under a certain confining stress. It's got a K naught of maybe 0.6. Starting stress ratio of 0.55 initially. Now that clay starts deforming. And it might have been deforming all along through creep, but maybe it's now starting to mobilize closer to its peak strength. So you're starting getting additional deformation. The overlying tailings is brittle. It doesn't follow that stress strain curve as easily, but because it's experiencing this movement beneath it, it starts experiencing a decrease in the horizontal effective stress, still under the same stress-controlled vertical stress. So you get that resulting stress path shown there. A couple of comments to add to that is we often look at these in isolation. It's just either rising phreatic surface or lateral extrusion or rapid loading. But really, if you look at a lot of the case studies, there's probably a combination of more than one, all leading to a high stress ratio. So we can have many things going on at the same time, or contributing to that kind of triggering mechanism. For example, you could have some creep from the underlying foundation soil, taking you up that stress path 1, and then a rising phreatic surface, and you're now really close to the instability line, so it doesn't take much of a rise to trigger the undrained shearing phenomenon. Alternatively, you could have the same initial basal extrusion, and then you place the waste rock dump or waste rock on the TSF very rapidly, again triggering failure. Or you could have a rising phreatic surface, taking you to a point where a small amount of basal extrusion can trigger it. So if people are going to be using trigger mechanism screening or trigger mechanisms to kind of screen out potential failure, I think it's incumbent to not just look at one in isolation and then another in isolation, but what can conceivably happen at the TSF. So is this then all we need to do? Is we screen this out? And I saw this a couple of years ago, where we know that a rising phreatic surface can cause triggering at a particular level of phreatic surface. So therefore, we ensure we've got enough piezometers to make sure that doesn't happen. Do the loading triggering? We screen that out. We know that we can control that. We make sure that we never place at more than such and such a rate. We screen that out. Maybe we don't have ductile foundations, and that takes care of itself. But if we do have a ductile foundation, we're going to put in inclinometers, etc., and monitor and get to a point where we can say, okay, we've got rid of that mechanism. So we've got rid of the rising phreatic surface trigger, we've got rid of the rapid loading trigger, we've got rid of the basal extrusion trigger. So it's all good, right? Well, I don't know. And this is probably a slide that is intentionally provocative. There's a phrase I've paraphrased here, and that is a philosophy that some people have advocated, saying, if the tailings can liquefy, assume it will. Now, 2 years ago, that was very, very commonplace way to be dealing with this whole problem. But we all know where that leads to. It leads to calculating post-peak strengths, sometimes using, I don't want to use the word dodgy, but using unverified or values that haven't been kind of cross-correlated with many methods. But that's an approach. If it can liquefy, assume it will. And what's implicit in that is saying, okay, so we've got these 3 trigger mechanisms that we've looked at in some detail, and we've kind of screened them out. And therefore, even if we have contractive tailings, we're confident that we're not going to get a failure developing. Given today's the election day, it seemed appropriate to quote a politician. You may remember this one. There's also the unknowns, the unknowns that we don't know about. Things we don't know. And what really brought this home to me in this context is the report on the Brumadinho failure that was done by the group out of Barcelona, the Politècnica de Catalunya, the SIMNI report, where they attribute that triggering to the advancement of a vertical borehole on the day the failure occurred, and the kind of increase in pore pressure around the zone of that borehole, and that increase in pore pressure propagated throughout the slope, and all the material which was probably in a very, very precipitous kind of stress state, we got that triggering. Now, it's hard to find a case study in the literature that has this as a failure mechanism, as a trigger mechanism. So, until maybe that report came out, maybe these were one of those unknown unknowns. Right? And there's people who don't believe that the Barcelona report. My personal view is that it's an incredible piece of work, and I find it very logical and very consistent, but other people perhaps disagree. But what it illustrated to me is that we can do these trigger analyses, but are we covering all our bases? And that's what scares me a bit. Is there something we've actually overlooked? And is there other trigger mechanisms that can then lead to that first statement? If it can liquefy, it will. And I don't think anybody's really got the answer to this at this stage. We're getting way better with the sort of plausible triggers and finding a way around it. But I think we're going to have a lot of valuable numerical modeling that's going to inform this particular debate. But I think that's where we are currently. And we're going to have to find a way to deal with this dilemma, because simply assuming it can liquefy leads us to building these multi-million-dollar buttresses, which, if they need it, they need it. But are they always really needed? Okay, so brittleness. Well, when is it static liquefaction? When is it just a little bit of strain softening? We try and think about it in our lab testing and so on. Is contractive undrained behavior can be true static liquefaction, rapid loss in strength, or less brittle contractive shearing, where brittle encompasses or encapsulates strain behavior as well. But then where's this division? Is it maybe a PI of 10? Is it some kind of measure of brittleness that goes beyond the Bishop index? I had a paper presented at a conference in Mexico about 5 weeks ago, and I'm waiting for the sort of clearance to circulate it. But that looks at post-peak behavior as well as the brittleness index to try and perhaps suggest another measure called the susceptibility index, which captures both those aspects, the strength loss and the strain over which it occurs. But we get this complete spectrum. We get the Fundar and the mountain polymaterial from forensic reports. We get the sand from Fundar. We get, as a comparison, that silica-fine sand again. And these are all isotropically consolidated. If we start doing K-naught consolidated, we get even more brittle behavior, as shown by that curve 1 there, going back to the ICOLD. That curve 1 is from Feijão or Brumadinho. It was K-naught consolidated, and you'll see a really, really small strain required to mobilize peak, and then massive strength loss over a small value of strain. So, wrapping up, and I'm going to kindly give Alecha about 4 minutes extra. So instability can be triggered by various mechanisms. We know that. If the tailings are at a state such that they're susceptible to contractive shearing, i.e. above the critical state line. And the greater the value of that state parameter, probably the more susceptible it is to triggering. But my view is that it's not clear that we're able to eliminate all plausible trigger mechanisms at this stage. And I hope I'm probably going to hear contrary views to that today, but that'll be great, because this is something that we're all struggling with, right? So hopefully we can get some debate on that. So I'm going to stop there. There is a few minutes, but rather than take questions now, I think Alecha said he would appreciate any spare minutes I can sent his way, so I'm going to do that. Okay. So thanks for that. We'll talk about this a bit more later on.
Thanks, Andy. I think we owe Andy a double clap there because he's now been through 8 presentations and now he can take a break. And Andy, we really, really appreciate your time and effort and your wisdom. And so thank you for traveling and being with us in person. We really appreciate that as well. I'm going to move on then to Paul Ridlen. Alejo's got the next presentation. So Paul was one of the authors of the bulletin. So he has a lot more inside knowledge as to what went into it, and particularly in terms of some of the appendices. And so I'm not going to say much more other than that Paul is also one of the ICOLD representatives in terms of the US, and he's also president of the KP branch in the US. So no further ado, you're going to talk to us about the flow chart. Thank you.
Okay, Andy gave Alejo 4 minutes and I'm going to take him away. So I'm going to apologize up front. I was given 15 minutes to give a 30-minute talk, and I'm going to try to get it to 25, but this is going to go over. But I think it's important to cover this. As Andrew said, I'm going to address the Appendix B of the Bulletin 194. And if I could real quickly, we've talked a lot about Bulletin 194, made several references to the Bulletin. How many of you are familiar with the Bulletin? Okay. How many of you don't have a copy of it? Raise your hand if you would. If you don't have a copy of 194. So if you're a member of SANCOLD, you can get access to the ICOLD website and you can download the preprint for this Bulletin 194. It is a good document. We're proud of it. And as Andy Small said, it's really showing a lot of influence around. Appendix A has been covered actually pretty well in yesterday's presentations and a few aspects of today. And then Appendix B is what I'm going to talk about today. And I would like to thank the reviewers, some fairly auspicious reviewers that we had that went over this, both Appendix A and Appendix B, including our esteemed Dr. Fourie and his colleague David Reed, and as well as the others that are mentioned here. We really appreciate their contributions. David Reed in particular had a lot of comments that helped to make the document better. In the main bulletin segment, you'll find this table 7.4, and it provides the recommended factors, minimum target factors of safety for 2 stability conditions. The static condition, which applies to both drained and undrained shear strengths, and then what we called in the bulletin the post-liquefaction condition. And I will say that, well, let me just say that to start with, these are minimum target values, and they're to be used unless justification can be provided for a lower value. And that's where Appendix B comes in, is providing a logical basis to deviate from these target minimums. And so what I said on the post-liquefaction, it's not my favorite term either. Andy has talked about he doesn't like residual strength. He's not alone in that. I tend to prefer the large strain terminology that Andy prefers as well. It worries me sometimes though that to be careful about that, because as you saw that stress strain curve from Brumagino, that large strain, you can actually have residual strength at small strains if you have a highly brittle material. So you should use this with caution and don't get too caught up with the terminology. I often call this the post-peak large strain, residual, post-liquefaction. So I use all the terms just to cover everything. The purpose of Appendix B was to provide a framework or a logical process to help understand where we're at in the universe of possibilities, and to select analysis techniques that are suitable for that reality, and to select these factor safety criteria. It's primarily for existing tailings dams, wherever contractive materials are present, either within the structural zone or supporting the structural zone. And I'll define what structural zone is here in a minute. And it's really, it's not prescriptive, it's really to provide guidance for making important decisions whenever these conditions occur. So even though it was developed specifically for existing facilities, it could be applied to new facilities if you have contractive soils or contractive materials in the structural zones. And it's important to note that whenever possible, we should eliminate contractive materials from our structural zones. And we certainly need to avoid using brittle materials. So to knowingly go into a design with a brittle failure mode is really not acceptable anymore. And so we should try to avoid them. And this applies both to materials in the embankments and also materials in the foundation. So if you have materials in the foundation that are subject to brittle shearing, brittle failure, then they should either be removed and replaced or modified in situ. But we recognize it's not always possible, or maybe at least practical, to remove all contractive materials, and therefore you can design against it, and that's why we feel like the approach can be used for new facilities. So I said I would define what the structural zone is. So this is a cross-section of kind of a typical upstream method dam. The same concept applies to other configurations, but we have a fair amount of emphasis in this course on upstream methods. So that yellow zone represents the outer shell that is the objective in a properly maintained upstream method dam, and that's either unsaturated so that it cannot develop excess pore pressures, or it's dense enough that it's dilative, so it might have been compacted during placement. And so that really forms the structural zone. And the structural zone is that mass of material that is required to hold back or retain the potentially liquefied contents of the reservoir, which, again, with an upstream method dam, are likely going to underlie a portion of that structural zone. And as Andy presented earlier, the Appendix B revolves around this flow chart on the right. And the flow chart on the right is based on, again, I think you've seen a few slides. It's trying to recognize and respond to this very wide range of stress-strain behaviors that are associated with contractive soils. And I guess the idea for this came from a statement in one of the papers by Peter Robertson, was that not all contractive soils are strain softening, and not all strain softening materials are brittle. And so that was a recognition that just kind of a broad catch-all phrase of, if it's contractive, assume that it will liquefy and assume that it can fail. It's more of a recognition that you need to understand the actual stress-strain behavior. And so the lower left-hand chart there that is from Appendix A is our initial kind of preliminary and interim characterization of brittleness. And it is trying to recognize that it's not just the brittleness index from Bishop that Andy talked about, which is shown on the right-hand axis, but it's also a recognition of the rate of strain, and was very happy to see that that sensitivity analysis that they ran with FLAC to show that the same level of strength loss would have a different result depending on the rate of strain. And so we tried to capture that in this framework. And so we apply this framework to the flow chart. And so the flow chart revolves around these 4 questions that lead to one of these 6 outcomes. And so we have 4 cases depending on the type of behavior. And then the 4th case, which is the highly brittle materials, is subdivided depending on whether the factor of safety is met and then whether there's a potential loss of life. So the 4 questions are: first, are contractive soils present? Secondly, are they subject to strain softening? If so, does the post-peak strength loss exceed 20%? And then finally, can the soils behave in a highly brittle manner? And so based on those, you have these different outcomes. And I'll walk through those as quickly as I can, and I'll try to get, again, within the 25 minutes that I said I would. So to start off with, I won't spend a lot of time on this, but this is the non-strain softening case. And so it would apply to either a plastic yielding situation where you shear up to a peak and then you deform at a constant volume. So that's the lower stress strain curve. And then on the upper end would be actually a dilative material, so that strain hardening case would actually be a dilative material. What I really need to do for future presentations is show like a quasi-steady state where you come up to a peak, then you dip down a bit, and then you start to strain harden again. That's really more the scenario that we're looking at. And so we apply the minimum factor of safety of 1.5 for both peak undrained and also for effective stress conditions, which we could talk about if we had more time, but I won't get into that. So the primary case here to consider is this peak undrained strength, as well as the drained condition, because depending on certain behaviors, the undrained strength could actually be higher than the drained strength. So in that case, a drained or effective stress analysis would catch that scenario. In this case, the residual strength or the post-liquefaction or the large strain case isn't really relevant because you never reach a residual because you don't have strain softening. So by definition, that analysis isn't really useful. Just keep in mind to make sure your strength parameters are appropriately conservative, and then also be careful at high stresses because you could have some particle crushing, which would also lead to contractive behavior. And so at high stresses, be careful about applying this. Okay, the case 2, I'm gonna have to walk through this one. Will take a little time because I need to walk through the math. So this is a case where you have strain softening with a brittleness index less than 0.2. So if you remember that brittleness chart, that's the green area or the upper area that is less than 20% strength loss at 20% strain. And so here the minimum factor safety of 1.1 for residual strength is very important. If your factor safety is greater than 1.1 and you have an appropriately conservative characterization, then the facility is stable. If it's less than 1.1, then you likely will need some form of mitigation. Here, the minimum target factor safety for peak undrained strength is 1.5, but if that cannot be met, then a factor safety of 1.3 could be acceptable in certain situations where it's not prescriptively regulated against. So there may be some regulatory requirement that does not allow you to use any factor of safety less than 1.5, or your owner may have some internal position that they are unwilling to yield on. But you ask the question, so why is a factor safety 1.3 acceptable for this case? It's not irrational, it's not arbitrary, it didn't come out of thin air. It's based on the observed behaviors that are represented by the stress strain curve. And so I'm going to just walk through a little bit of a derivation here as to how we got to that logical conclusion. So if you'll think back to the brittleness index, which is the peak strength minus the residual strength divided by the residual strength, or divided by the peak strength. And if you apply basic mathematical principles, I'm not going to walk through them step by step, but you can read that in the paper or in the presentation. You get to an outcome of peak strength is equal to 1 over 1 minus the brittleness index times the residual strength. And so then if you divide by residual strength, you get the ratio of peak strength to residual is equal to that ratio of 1 over 1 minus 1 I sub b. And that's can be defined as the sensitivity ratio. And I just use sensitivity because it's easier to plug into these later equations. And so if you have a brittleness index of 0.2, you can do the math. You get a sensitivity ratio of 1.25. If you have a brittleness index of 0.1, you're going to wind up with a ratio of 1.11. And so now if you can think, one of these days I'll have an example of this, but if you think of a homogeneous embankment, or maybe one of those examples that Andy presented in his talks just now. And so if you'll accept that the ratio of peak to residual strength, i.e. the sensitivity, is going to imply that the factor of safety at peak strength is going to be proportional to the ratio of the factor of safety at peak over factor of safety at residual is going to be proportional to that sensitivity ratio. And so if you have a brittleness index of 0.2, therefore your sensitivity is 1.25, and you start with a calculated factor of safety of 1.1, then multiply that times 1.25, and the behavior is going to lead you to a factor of safety of calculated of 1.38 for the peak strength. So if you just plug the numbers into the limit equilibrium analysis and nothing else changes, these are the results that you're going to get. So in this case, the factor of safety for peak is greater than the 1.3 criterion, and you've also met the residual strength. So the residual strength is the controlling case. If you just started with a factor of safety of 1.3, and you calculated that, and then you changed the value to the residual strength, and nothing else changes, you're going to calculate a factor of safety of 1.04, which is going to be less than 1.1, which means you'll need to modify the slope to achieve 1.1, and then when you calculate the factor of safety for peak, you're going to get 1.38 approximately. And again, if you don't believe me, go home and run an example case, and if you find a different result, let me know. Just send me an email. So if we're starting with a 1.5 factor of safety, that implies a residual strength factor of safety of 1.2, which is great. That's greater than 1.1, and if you can live with that, that's better. That's wonderful. And so it means you're at a higher level of safety. But if you can't meet that, and our minimum criteria is 1.1, then the peak minimum of 1.3 is acceptable. And I've gone a little bit on and on about this because this will get challenged. I've argued with some really smart people who insist it must be 1.5 all the time. And I don't think that's necessary in cases like this. But it is important to note to calculate the factor of safety for all three loading conditions. I've heard people say residual strength is not very informative. The residual case is not very informative. It's too conservative. If you have a brittle material, as we'll see here in a minute, it is essential to consider that. And also, it's important to make sure that residual strength is a truly minimum value. I just kind of drew in kind of a solid line there. I would much rather see that stress strain curve kind of taper off and become horizontal. I don't like to see that continuing to decline, so you need to use some judgment in picking your residual strength. Okay, now for case 3, which is where we're starting to get into a higher level of risk and uncertainty. And so again, we're in the range of 0.2 to 0.4 brittleness index. Again, the minimum factor of safety of 1.1 using residual strength is very important. If you're greater than 1.1, then it's stable. If you're less than 1.1, there may be some value in running a deformation analysis because of the limitations of limit equilibrium that were presented, and it may be possible that if you have a marginal factor of safety, that the deformation analysis may be useful to demonstrate that ultimately failure won't occur. And that really kind of goes to that definition of the limit state versus deformation-based criteria, if you will, that Andy talked about, that the deformation is a better representation of what really matters. The limit state is a simplified approach. Now the ICOLD table 7.1 or maybe 7.4 actually recommends this factor of safety for peak conditions greater than 1.5. And now here it's important to note, and this has been said before, and actually Dr. Morgenstern said sometimes factor safety 1.5 is okay. and sometimes it's not high enough. And this is a case where a 1.5 would not be enough. So if you apply that logic I just walked through for case 2, and now we have a sensitivity index of 1.67 that corresponds to our brittleness of 0.4. And so if you have a factor of safety of 1.1 and multiply that times 1.67, you need a 1.84 in order to meet both criteria. And in other words, if you started with a factor of safety of 1.5, divided it by 1.67, when you ran your residual analysis, you're going to be less than 1. And so that's not going to be acceptable, and you'll have to buttress your facility or flatten your slope or modify it. And what this really does, in my opinion, is it demonstrates the importance of this residual strength calculation, and it also demonstrates the fallacy of relying on a 1.5. And this is again where I've had these arguments with people that are way smarter than me, but I think kind of get lost in taking a very hard, adamant position that we must have a factor of safety of 1.5 when the 1.5 is not always going to be adequate if you have brittle conditions. And so moving on to the cases 4, where you have a brittleness index greater than 0.4 or a greater than 40% strength loss. And, you know, you could go and do, I have in previous analyses gone through the same type of analysis that if you have a brittleness index of 0.8, you may need a factor of safety for peak conditions greater than 4. And so it's really kind of drives home that in cases where you have highly brittle materials, understanding this residual strength factor of safety and really understanding the characterization, making sure you have a fairly high degree of confidence in your characterization. And if you do have a high degree of confidence and you still have a factor of safety less than 1.1, then you have a real problem that you have to address. So for initial screening analysis, it's appropriate to consider a near lower bound. What is near lower bound? I'm not going to tell you what the number is. It might be a 5th percentile, a 10th percentile, but certainly not greater than a 20th percentile value for that residual strength. And so again, the concept is if you're using a conservative value and you have a factor of safety of 1.1, then you can be expected to be stable. If you have less than 1.1, it doesn't necessarily mean that failure is certain. And so therefore, again, a nonlinear deformation analysis may be useful to understand that. However, if you look at the last bullet there, if your factor of safety is much less than 1, so if you have a factor of safety around, say, 0.5, it's unlikely you're ever going to solve that through a deformation analysis. And the probability of a flow failure is probably pretty high because that's the condition that would correspond to, say, a Brumagino before it failed, is the residual strength factor of safety was about 0.4 to 0.5 there. And here, again, the ALARP principle, I don't really have time to go into ALARP, but the ALARP principle is important, and it basically boils down to, are you doing everything you can to minimize or eliminate the risk and avoid potential fatalities? And, you know, one thing that, you know, in applying these factors of safety, I just threw up here a factor of safety of 1.5. What we're trying to do is keep our mobilized shear strength low enough that we're not getting close to that peak. And again, Andy and Luis has talked about this already, that when you have a highly brittle material, when you get up close to that peak value, which is occurring at a low strain level, remember, it doesn't take much to push it over the edge. So what we want to do is keep our mobilized shear strength well below. And so if we have this factor safety of 1.1 for a brittleness index of 0.4, then we're somewhere around a factor safety of 2. It's actually, I just showed 1.84. And so what we're doing is keeping our mobilized shear stress about half of the peak value in order to limit our strain. And the reason that many people, especially owners, get very nervous when they have highly brittle materials and they're applying this factor of safety 1.1 is the mobilized shear stress is down there where that red arrow is pointing. And so that means that your factor of safety for peak conditions, again, might be 4. So they're going to look at that and say, you're being way too conservative. A factor of safety of 4 is unrealistic. But the problem is, if you truly have a brittle material and you go over the peak, that is disaster. And that's what we again saw from Brumagino and others. Wish I had time to go through this, but I don't. But you're going to see examples of nonlinear deformation analysis this afternoon. And it is, you know, a lot of cautions that should go along with that. Tom and I were talking about this at the break about there's a lot of potential with nonlinear deformation analysis, but it's a case of garbage in, garbage out. So if you don't understand what you're putting into the model and it's not well developed, then it will be of limited use. And that's all I'll say on that. Also, don't really have time to go into seismic loading. Andy Small has covered a bit of that, but there's guidance in the bulletin and in Appendix B on how to approach seismic loading for these different cases. And with that, I picked up 2 minutes of my revised 25-minute target. Thank you very much.